Okay, in this next series of videos here, we're going to be exploring gravitation in particular and central forces in general. We'll start with some background from planetary mechanics here. A lot of the data that feeds into understanding gravity comes from astronomy. And if we start back with ancient astronomers, they observed that the sun's motion in the sky followed a 24-hour pattern. And the general assumption that was made was that the sun moved around the Earth, which we call geocentrism. Now, that's not to say that there weren't people who thought that heliocentrism was a better idea, Earth going around the sun. Chief among those was a fellow by the name of Aristarchus. Problem though with his model, as the ancient Greeks saw it anyway, was that if the sun was stationary, then in order to have the apparent motion of the sun in the sky, you would need the Earth to rotate on its axis once every 24 hours. Well, they knew the diameter of the Earth. That was something that they were able to get by looking at the um, angle of a shadow cast in one part of the Earth, while at another part of the Earth the corresponding shadow was of no size. This could only be done between the tropics, where twice a year you have what's called a zennial crossing, where the sun is directly right down on top of something, so you'll have a brief moment where it casts no shadow. At that time, a known distance to the north, a rod was casting a shadow. They could work out the angle. That was the difference in latitude between the two locations. They knew the distance, and from that they were able to extrapolate the diameter of the Earth. So they knew roughly how big the Earth was, and if you work it out at any reasonable latitude, it turns out you are moving awful darn fast. And so the objection they had, which they couldn't resolve, was, well, if that's the case, wouldn't you be having these horrendous winds that would make a hurricane seem like a gentle breeze? So then everything should be just totally flattened out. So even though they agreed that the heliocentric model would seemingly work better for understanding the motions in the sky, they felt that experimental evidence belied that. It took the realization, you can ultimately say maybe blame Torricelli for the final confirmation, but it took the realization that the Earth's atmosphere, for all practical purposes, is non-existent. Sort of a good rule of thumb is that if you want to fly an airplane versus flying a rocket, sort of the altitude limit there is about 100 kilometers. So given the comparison of that to the radius of the Earth, and then the breathable portion of the atmosphere is much thinner than that. If you were to take the Earth and shrink it down to a size of an orange, the atmosphere basically is about the thickness of the orange part of the orange, not including the nasty white bit underneath the orange surface. And so what happens is when the Earth rotates, it just drags its atmosphere along with it, since for practical purposes there's effectively no atmosphere, versus the implicit assumption that the Greeks were making that the universe was full of atmosphere. Those are always the most dangerous assumptions that you make, are the ones that you don't even realize you're making. Okay. So anyway, it was also observed that planets moved in circular, well, we'll modify that in a moment, but it seemed the planets were moving in circular paths. There was a problem though, And that is if you look at successive nights in the sky, you'll find that each night a planet typically is located a little further east than it was the night before, except every so often it will head for a few days in a westward direction, and then return back eastward. In fact, that's what gives it its name. Gives planets their name. The word planet is based on the Greek word for wanderer. To explain this motion, an idea called an epicycle was introduced. So with an epicycle, you have the planet going about in its orbit like so, but that's not really the planet's orbit. That is the deferent of the epicycle. And then the planet is actually going on a little circle attached around the middle. So think of it like, one of those little like some little toy or something like that, where it goes around on a track, but it's also spinning around, and then the planet is attached on the end of that. So this allowed the retrograde motion to be explained as a physical retrograde motion. Now, as observational data got better and better and better, you had to start tweaking these epicycles to match the observed data. You started creating equants and stuff like that, and you kind of create these stutter stepping motions that the planet would take around in the epicycle. Sometimes you even nest another epicycle on top of another one, and it got to be a real mess, and trying to follow it got very indecipherable. So this is when Copernicus reintroduced the idea of heliocentrism. The big motivation was that it provided easier computation. So now that being said, Copernicus still mandated a circular orbit. He did require an epicycles, but they were smaller, much smaller, and much simpler. So it seemed like at the very least he might be onto something. But certainly, if you're debating between the two approaches, you wouldn't necessarily say that the heliocentrism was all that much more awesome. It seemed computationally cleaner, but it wasn't like it was really just screaming, oh, look how simple, as we usually like to portray it. Now, this got extended. The important fella here is a guy by the name of Johannes Kepler. He went over data from his graduate advisor Tycho Brahe, and over a period of a couple of decades deduced three key patterns about the motion of the planets. He also picked up a fourth one, which turned out to be nothing. But there are three that have stuck. And one of them is the realization that the orbits of the planets are elliptical. Now, you shouldn't really get excited about this, because if you look at, this was hard for Kepler to deduce. If you look at the orbit of the most eccentric planet we've got, Mercury, or the second most eccentric planet, Mars, if I were to just draw the orbits without a coordinate axis, your eye would be deeply challenged to discern it from a circle. It took Kepler a lot of work, and it took a lot of really good unaided eye observations for Kepler to work out that he was staring at ellipses and not circles. So it's actually quite an achievement. But that explains Copernicus's tiny epicycles. What that epicycle was really doing was just turning a circle into an ellipse. So there was that. Okay, so with that as background, in part what I'm going to be doing with this series of videos is treating this as a case study for how the actual work of theory gets done. Now I will start by kind of giving away the store and then coming back later and trying to reverse engineer Newton's reasoning. But let's go ahead and start by giving away the store. So let's go and take a look at Newton's picture. Now Newton had Kepler's Kepler's phenomenological observations, and he realized that that was something that he would need to fit into a model of gravitation. So Newton's big realization was he said, okay, let's say I put a suitably large cannon on top of a planet and I fire it. He reasons, okay, if I don't put that much powder in it, it's just going to go like that. A little more powder, obviously we're talking ludicrous amounts of powder, it'll go more like that. Then maybe more like that, and you can start to see what's happening as it is falling towards the center of the Earth, but the Earth itself is curving out from underneath. So he reasons that you should eventually have a magic speed such that if you fired it, it would go back and hit the cannon on the backside, assuming no air resistance. So this is why it gets called Newton's law of universal gravitation. Is that his reasoning here is that the same force that makes apples fall to the ground puts planets into their orbit. It wasn't obvious that those were the same force. In fact, there was sort of a philosophical dichotomy between what was happening near the surface of the Earth and what was happening in the heavens. So that's why it's a big deal, and that's why it's Newton's law of universal gravitation. By the way, this little illustration that we've just gone through here with the cannon, this is an example of a thought experiment, or in German Gedanken experiment. You'll hear physicists say both. And it's a tool that theoreticians use to help reason through the situation they're analyzing. So they're not actually necessarily building, thinking for real about building the apparatus, but they're using it to reason through the consequences of their theoretical models. Okay, anyway, his result that he gets after all this work is that if I have any two particles, I, so it's the mass of particle I, and this is the mass of particle J. So for any two particles, I and J, the force on I due to J and the force on J due to I, like that. And let's call this distance here, we'll make it a vector actually. This is a position vector that points from I to J, and so we'll call that Rij. So it's the position vector that goes from I to J. So the Newton's law is Fij equals G mi mj over Rij squared times Rij the vector over Rij the scalar. All right, now what we've done here, and this is certainly a matter of taste how you write it, this is one way that you can write it. What I've done here is in parentheses, I've constructed a unit vector. So I could have just as easily chosen to write this as Rij hat, the whole thing in parentheses. I could have chosen to write as Rij hat. That's actually something I prefer, but a lot of texts don't do that. And if you're to do that, your Rij hat would be a unit vector that points from I to J. In fact, a lot of books up the ante and go the other way. They will actually write it, and I'm just kind of putting this off as an aside here. You'll often see it written as like an Fij equals GMIMJ over Rij cubed times Rij, the vector. And took, at least for me, it took me the longest time to really be able to just look at that and say, oh, I'm looking at an inverse square law force. Because one of these powers of Rij is there purely to construct the unit vector. So, like I said, my attitude is write it with the unit vector. The second best choice is explicitly construct the unit vector even if you have to write Rij twice in the denominator. This is just, I mean, it's legal, but I don't think it's the clearest thing. All right, so let's go and take a look at our model of Newtonian gravity and see what we get out of it. One of the things we get is that it is a central force. What central means is that it's directed center on center between the objects. So it's directed on the line that connects the objects. That's a central force. That's as opposed to, say, magnetism, which acts, at right angles to the velocity of the object. Just to give a totally different example. You'll notice that it depends on the masses. This is actually very important. If we want this to explain apples falling near the surface of the Earth, because F equals ma, the force law needs to have an m that cancels out. And also, in order to respect the third law, the mass of the other player then also has to be in there, so that you get the same magnitude of force regardless of which player you're computing it for. So we can extract out the magnitude of the gravitational field near the surface of the Earth. We get that the gravitational field strength is g times the mass of the Earth over the square of the radius of the Earth. And you can get that by, say, putting in a rock for one of the masses, and then when you do F equals ma, the mass of the rock cancels, and then this is all that's left. Okay, so that's all well and good. Now, you'll notice that when I did this bit with the gravitational field, and we'll be more careful about it in a bit. I did this bit about the gravitational field strength. I just used the square of the radius of the Earth as if I could treat the distance between me and the Earth as the Earth's radius. Now, I'm not going to be strung out about adding an extra meter or so for my belly above the surface of the Earth. That's not the issue. The issue is, can we, it makes sense, like say if you're looking at the Earth and the Sun, they're so far apart compared to their sizes, they basically act as geometric points, so treating them center on center seems totally legit. But for me to be right next to the surface of the Earth, and then treat the Earth as if it were a point mass concentrated at the center of the Earth, that's a little less obvious that you can do that. So one of the things Newton had to show was the force for a uniform shell, so this gets us to the shell theorem. All right, so here's how it goes. Newton realized you don't have to prove it for the Earth, you only have to prove it for a shell of the Earth, and we'll treat it as of uniform density. Then we can construct the Earth by a nested collection of these shells, and they don't have to be the same density either, which is good because the density of the Earth changes as we descend. It gets greater. So, let's go take a look at a shell of the Earth like so. All right, now let's try to touch that up just a little bit. There, much better. All right, so we're taking a look at a shell of the Earth. Now, we'll call the point here in the center. That's going to be our origin. And we will say that the Earth has a radius big R. Okay. Now, I'm going to be interested in analyzing the force from this shell at some point P outside the shell. And we'll say that this distance between the center of the shell and the center and the point at which I care, we'll say that that distance there is little r. Okay. We'll also say that the shell that we're looking at has the surface mass density sigma should be equal to the mass of the shell over its area, 4 pi r squared, like so. All right, this point right here, let's go ahead and call that Q. So if I look at just a small differential of mass situated at Q there, we're going to feel a gravitational force due to it, dFq, like so. And we'll go ahead and say that this distance here is S. All right then. And we'll connect that out there too. This is badly drawn, sorry. Let's try that again. So that distance is S. There. That distance is R. We'll call this angle here theta, that angle there phi. All right, now the dfq is pointing off at some angle phi, but that's not a big deal. All we need of it is its x component, like so. And that's because what we can do is we can imagine looking at a thin strip. Like so, of mass dm, like that. And so then we'll be left with a differential force dfx. And the game will be, we'll integrate over all the strips to get our force. And we can do this because, you know, for every mass element I have up here, I've got a matching one down there that cancels the vertical and the in and out of page contributions, and all we have left is this inward contribution. Okay, so nothing left but to actually start to calculate it out. So first bit here is we need to express our differential of mass dm. All right, so to do that, it'll be equal to the surface mass density. Now it'll be equal to the area of this thin band here. So they'll be equal to its circumference. So it'll be 2 pi times its radius, which will be r times the sine of theta. So 2 pi r sine theta. So that much there is the radius of the band. And then the thickness of the band here, this horizontal bit right there, that's just going to be r d theta. We can, if we need to here, let's go ahead and draw in a d theta so that we can understand that a little better. And let's make it thin so we can still see everything else. There we go, like that. So this angle right there would be my d theta. All right, so the thickness will be r d theta. So we get that the differential of mass we've got there is sigma times 2 pi r squared sine theta d theta. Okay, now our differential of force, dF, well, that's equal to the dfx that we just identified. So that will be equal, by the law of universal gravitation, to gm dm over s squared. And then I need to take the x component, so I pick up a cosine phi. All right, so then if we substitute in the dm that we have, we're left with gm sigma 2 pi r squared sine theta cosine phi d theta over s squared. Now, we have a bit of a pickle here. We can pull out some constants as we look to doing our integral here. So f will equal g 2 pi sigma r squared. Now, I think integrating over theta is what's going to make the most sense. We'll be integrating from 0 to pi. Okay, that's all good. So we'll integrate 0 to pi d theta. I have a sine theta cosine phi over s squared. Now, I can't pull out the cosine phi or the s because both of those implicitly depend on theta. So I'm going to have to work on both of those in turn in order to get this all in the same terms. This is going to involve me invoking the law of cosines twice. So first we're going to take a look at s. So by the law of cosines, that would be r squared plus the big R squared minus 2rr times the cosine of the interior angle cosine theta. So that's exactly what we're going to observe. So by the law of cosines, we have that s squared is equal to r squared plus r squared minus 2rr cos theta. All right. And actually, what we're probably going to do here is rather than integrate over theta, conventionally looking ahead to coping with the phi, since the phi is also going to end up with an s in it when we do the law of cosines on it, it's going to make more sense to do a change of variables to s. So we'll differentiate our law of cosines. So 2s ds will equal constant, and then derivative of cosines minus the sine cancels the minus sign. So we're left with 2rr sine theta d theta. Can cancel the 2's for what it's worth. So I will rework this for d theta, stick it into here, and then since I will have, and so I'll get an s ds over rr sine theta. That's all cool. The over sine theta cancels that sine theta. That's good. And then the rr will cancel this little r and one of the big r's. And then I still have an s upstairs. That cancels one of the s's downstairs. So a lot of bang for your buck with that substitution. So we get f equals g m times 2 pi sigma big R over little r. Over little r. Integral over ds now of cosine phi over s. We're integrating from r minus r to r plus r, like so. Okay. Oh, my bad there. Where did that one rogue little r come from? Right here. That shouldn't be there. Okay, much better. All right, now this is all well and good, but the phi still depends on s. And so I will need to rewrite that in terms of s, and the law of cosines will come to our aid there as well. The way to set this one up is we'll write it for big R squared. So then it'll be little r squared plus little s squared minus 2rs times the cosine of phi. So we'll have r squared equals r squared plus s squared minus 2rs cosine phi. So we can rewrite that as cosine of phi equals s squared plus little r squared minus big R squared over 2rs. Okay, so now we can substitute in for that. The numerator is going to have to stay inside the integral, nothing we can do about that. But we can pull a 2 and an r out. The 2 will cancel the 2 and the 2 pi there, and then I pick up a power of r, little r squared now. So now we have f equals g m pi sigma r over r squared integral minus r minus r to r plus r ds of s squared plus r squared minus r squared over s squared. All right. I have to admit, normally I would be lazy enough that I would just immediately start trying to look this one up, but what the heck, let's try to do a little better job. So gm pi sigma r over r squared integral ds r minus r plus r, whoops, r plus r. I can at least divide through by that s squared. That'll help. 1 plus r squared minus r squared over s squared. So I actually end up with two integrals. And we'll evaluate them in turn. So gm sigma, oops, gm pi sigma r, that's supposed to be a sigma there. There we go. Over r squared. Integrating 1, that's going to give me r plus r minus r for that term. And then from this term, the r squared minus r squared is a constant, and I'm going to get minus 1 over s. So this will give me minus r squared times 1 over r plus r minus 1 over r minus r. Cool. All right. So for what it's worth, the little r's here cancel, and I'll get a 2 big R there. And then here, so what we'll get is, we'll write it as equals g m pi sigma r over r squared. Then we'll write this as, so we have a 2r minus. Now here what we're going to do is we're going to do a little factoring. We can factor this as r plus r times r minus r. And then this will be 1 over r plus r minus 1 over r minus r. Now by doing that, I multiply that in. For this term here, I'll be left with the r minus r, and this term here leaves me with the r plus r. So I get g m pi sigma r over r squared. I have a 2r minus r minus r minus r plus r. All right, so again here, I end up here canceling my little r's again. And this is minus big R minus big R, so it's minus 2R, but that's minus that, so that becomes 4R. So I can put that in. Again, that's a really badly drawn sigma there. There we go. So finally, I am getting Gm times 4 pi sigma R squared over R squared. Now this bit right here is the mass of the shell. So that gives me G times the mass of the shell times the mass of times our point mass over R squared. Oh, thank God, that's exactly what 2 point masses look like. And so yeah, point mass interacting with a shell acts like 2 point masses, and as far as that goes, 2 shells interacting with each other look like 2 point masses. So the moral of the story here so far is that outside the shell, it acts like a point mass located at the center. All right, now for inside the shell, the analysis is the same, except you will show that the limits of integration are now going to be with the big and the little r's flipped. So after you show that, you will get Gm sigma R squared over R squared integral R minus R to R plus R ds times 1 plus R squared minus R squared over S squared. And when you do this one, that turns out that you'll do the similar algebra to what I just did. Oops. And you'll get to a point where you have F equals Gm sigma R over R squared times 2 little r minus 2 little r. And you go, oh, that's 0. So inside the shell, it exerts no net gravitational force. All right, and that is what allows us eventually to get to that now retroactively justifies us saying that the gravitational field near the surface of the Earth is G times the mass of the Earth over the radius of the Earth squared, which is approximately 9.8 newtons per kilogram. All right. In the next video, we will take a look in more detail at Kepler's laws of planetary motion and what sense Newton made of that to get the form of universal gravitation.